On April 10, 2019, the European Commission, together with the Event Horizon Telescope collaboration, unveiled a never-before-seen sight from the universe. A vision from a remote galaxy, a staggering 53 million light-years away. Our focus is drawn to this, the heart of the distant galaxy M87, the very first image of a supermassive black hole. This remarkable unveiling gives solid proof of this celestial entity, which until then were only a concept. It allows scientists to measure the black hole's mass more precisely. Who could have guessed that the shape of a black hole is round, exactly as forecasted by Einstein's theory of relativity?
Long ago, we didn't know if black holes would be common in the centers of galaxies. With the help of the Hubble telescope, which has good, precise ways to look down in the center, every galaxy we've had the capacity to check has revealed a black hole to us. Thus, we will extrapolate and assert that a black hole is a natural phenomenon in the center of all galaxies of the universe.
We're ready to delve into the structure of a black hole, an exploration that might reshape our comprehension of the cosmos. Join us on this journey as we seek answers to one of the most important questions in astronomy. Black holes are extraordinary cosmic events that are born out of massive explosions. Their mass is concentrated into such a tiny space, which creates gravitational forces of immense strength. It's so extreme that nothing, not even light, can escape. Once something enters a black hole, it's there to stay forever. These gravitational powerhouses vary in size. Stellar black holes, for instance, are a few times the mass of our sun. On the other hand, supermassive black holes can possess millions or even billions of times the sun's mass. These immense objects not only warp space with their mass, but also deeply influence how time flows around them. Understanding this brings us to the core idea of how they interact with the fabric of space-time, which is based on Einstein's special theory of relativity. This theory suggests that space and time are woven together into a four-dimensional space-time continuum, with 3 dimensions for space and 1 for time. When we introduce mass into Minkowski space, something special happens due to the way energy interacts within it. Einstein's theory tells us that space isn't flat, just as Minkowski space suggests. Instead, it bends around objects. So in this view, gravity isn't just an invisible force acting over a distance, it's actually the result of the curvature of spacetime. With this term being the curvature tensor, and this one is the energy density tensor. We can observe that the curvature of spacetime increases with an increase in energy density. As gravity is an effect of the curvature, the more energy an object has packed into it, the stronger its gravitational pull becomes. And this is the fundamental reason behind the theoretical concept of a black hole. This incredibly dense object forms when a massive body collapses to a specific size, something known as the Schwarzschild radius. General relativity not only forecasts the existence of black holes, but also outlines their structure through the Schwarzschild metric. This metric is a specific solution to Einstein's field equations. If you're overwhelmed by this equation, don't worry, I've got a simpler explanation for you. You see, this equation predicts that a black hole has 2 parts. The event horizon, which behaves as a boundary between a black hole and the rest of the universe at this radius. The singularity, where the entire mass of the black hole is predicted to exist.
You can think of a black hole as completely consuming the volume of space-time in its vicinity.
If we're talking about how this was formed, it all starts with the death of massive stars. These stars go through a supernova explosion, a powerful and cataclysmic phase to their life cycle. During a supernova, the star's outer layers are violently flung into space, while the core undergoes a gravitational collapse. But not all of these events have the same outcome. If the core's mass is several times that of our sun, gravity's force overwhelms everything else, inducing the core to implode. This implosion is so severe that it shrinks the mass into an incredibly tiny volume. Think of it like squeezing a softball. When you squeeze it, the ball shrinks, but its mass, or the amount of material, remains the same. It just becomes denser. Now imagine you could squeeze that ball until it was as small as a grain of sand, yet it still weighed as much as before. This is similar to what happens when a massive star undergoes a supernova.
I don't think a black hole knows it's a black hole. It's just a lump of mass out there If Earth today turned into a black hole, it'd be a mini black hole like the size of a plum.
Have you ever wondered why matter doesn't run out of space when it collapses during the formation of a black hole? Is there a point where it just can't be compressed anymore? Well, there is a limit to how much you can compress it, and this is connected to the different states of matter. For example, a rock maintains its rock shape due to the forces between its atoms and molecules, something known as electric forces. However, when under a lot of pressure, it can push atoms and molecules closer together. This squishes the space between them, a situation called electron degeneracy.
You're trying to cram electrons into the space of other electrons, and they don't allow that, all right, from quantum physics. They keep their own identity within the structure.
This state of extremely dense matter can be found in white dwarfs, which is the remaining core of a star like our sun. Consider the massive space between an atom's nucleus and its electrons. If an atom were the size of a football stadium, the nucleus would be a tiny poppy seed at its center, and the stadium walls would represent the electron orbits. This fact was uncovered by Ernest Rutherford. In his experiment, he shot particles at a thin layer of gold. What he found was that most of the particles zoomed straight through, as if there was nothing in their path.
The next morning, he is rumored to be afraid to step onto the floor, getting out of bed, that he might fall through it, because he alone knew how empty matter was.
The next stage of compression is cramming the electrons into the protons. The outcome of this high-pressure interaction, where a positive charged proton combines with a negative charged electron, is the creation of a neutral particle, something called a neutron. You might recall something as neutron stars. This name isn't random, since it's directly connected to the fact that these stars are densely packed with neutrons. What remains after a star has exhausted its life cycle is such a neutron star. These celestial bodies are incredibly dense. In fact, it's the densest known objects in the universe that aren't black holes.
Neutron star matter weighs about a mountain per teaspoonful. So much that if I had a piece of it here and let it go, and I could hardly prevent it from falling, it would effortlessly pass to the Earth like a knife through warm butter.
Neutron stars that rapidly rotate have magnetic fields that pulse. We call those pulsars. The person who discovered pulsars, Antony Hewish, won the Nobel Prize for it in the 1970s. So how dense is a neutron star? Imagine taking a herd of 300 billion elephants and cramming them into a thimble. Once you've achieved the density of a neutron star, compressing the matter any further plunges us into the territory of black holes. Black holes can vary in type and each possessing its own distinct size, formation process, and behavior. The most prevalent is the stellar black hole. Its mass spans from 3 to 10 times that of our sun. These form when a massive star exhausts its nuclear fuel and falls inwards under its own gravity. The star then shrinks incredibly, packing a vast amount of mass into a minuscule volume. Typically, these black holes carry a mass several times that of the sun, yet they're astoundingly small, just a few kilometers across. This makes them extraordinarily dense, forming an event horizon. Then there are intermediate mass black holes. The exact mass of these black holes is uncertain, but it's thought to be in the thousands to tens of thousands times that of the sun. And so, they're denser than stellar black holes. How they form is still a puzzle, but there are two leading theories. One proposes that they result from several stellar mass black holes merging together. The second one suggests that they might originate from massive gas clouds in the early universe, collapsing inward to create a black hole instead of a star. Locating these intermediate mass black holes can be challenging, but there have been some indications of their existence observed indirectly, like observing the behavior of stars and gas near suspected locations of these black holes. At the top end of the scale, we have supermassive black holes. These are the big players, with masses millions to billions of times that of the sun. They sit in the centers of most galaxies, including our Milky Way. We're still not sure how these form, but one theory is that they grow from smaller black holes by continuously sucking in matter from around them. Last but not least, we've got charged black holes. These are interesting variations of black holes that have an electric charge. There are two main types, Reissner-Nordstrom and Kerr-Newman black holes. Reissner-Nordstrom black holes carry a charge, but they don't spin. General relativity describes them using what's called the Reissner-Nordstrom solution. Their charge influences their gravitational field, but in most ways, they're like uncharged black holes. They have an event horizon, but its size depends both on the black hole's mass and its charge. Kerr-Newman black holes, on the other hand, both carry a charge and spin. They're described by the Kerr-Newman solution in general relativity. The mix of charge and rotation creates unique phenomena around these black holes. One such effect is frame dragging, where the spinning black hole pulls and twists the surrounding spacetime. Other than the event horizon, there's another boundary known as the Cauchy horizon. This is an inner edge inside the black hole, which marks the spot where the singularity is located. Now, you might be wondering, what's on the other side of the black hole if you cross this horizon? There are compelling theoretical ideas about what might transpire if you were to survive a journey through a black hole and emerge on the other side. Our equations suggest that an entirely new space-time dimension would unfold before you. According to the Schwarzschild equation, when we're still outside a black hole at some distance, we find that ds squared is greater than 0, meaning we're dealing with a time-like space-time interval. In this region, cause precedes effect, and the laws of physics hold as expected. But the moment we cross the black hole's event horizon, something very bizarre happens. The crossing subtly changes the signs in the metric, flipping them from plus minus to minus plus. This sign change in both of these terms means that dt switches from being a time-like to a space-like, and dr switches from being a space-like to a time-like separation. What's strange is that time can now move forward, backward, or even stand still, while space must progress forward, just like time did outside the event horizon. So yes, to answer the big question you've probably wondered, what happens inside a black hole? According to this equation, once you're inside, you're in a completely new space-time dimension, where space becomes time and time becomes space. And now for the question you might not have thought to ask. How does this swapping of space and time affect someone falling into the black hole? Well, normally we can control how we move through space, but unfortunately not through time. I can decide to fly toward a black hole or away from it, but I can't stop myself from aging into the future. So once a person falls past the event horizon, he can't choose to move away from the singularity. But one thing for sure, he can still pick a path by adjusting his trajectory through time to get there. So if we think of the singularity as a point in space, he loses the ability to change direction, but gains more control over time. And by time, I mean someone accelerating toward the singularity will age less before reaching it compared to another person simply free-falling toward the black hole. In the end, the singularity here isn't a place in space, it's a moment in time. And once you've crossed the event horizon, there's no going back. The singularity is your inevitable fate, just as 12 a.m. tomorrow is unavoidable in normal space-time. Some even speculate that passing through the singularity might open a portal to another realm. So is every black hole its own universe? In physics, a singularity refers to a point in space-time where certain quantities become infinite or undefined. We find such singularities in multiple theoretical contexts, such as at the inception of an expanding universe known as the Big Bang singularity, and also within black holes. When examining the Big Bang singularity, a significant challenge arises. The theory suggests that our universe emerged from an incredibly dense and hot state, approximately 13.8 billion years ago. But as we trace time back to this initial state, the equations of general relativity fail. This suggests that our current understanding of physics can't fully describe the conditions at the Big Bang. So to resolve this, we need a theory that combines general relativity and the principles of quantum mechanics.
When you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now.
According to Einstein's theory of general relativity, anything falling into a black hole, be it matter or energy, encounters this singularity. It experiences something we call infinite compression. This concept really stretches what we currently know about physics. The idea of infinite compression is tough to wrap your head around, but one way to imagine it might be through the movie Interstellar. We see Cooper plunges into a supermassive black hole gargantua. The screen erupts in a vortex of light, which represents a visual of space-time being distorted. Once inside, he finds himself in a realm beyond normal comprehension, a space-time region that represents every moment in his daughter's bedroom all at once, a tesseract, if you will. This is a good depiction of how time and space might behave differently in the presence of a singularity.
Center black hole is a singularity. All the theories say the matter occupies zero volume, thereby having infinite density. That's a limit of Einstein's theory. That's where it breaks down. So in Einstein's equations, we're dividing by zero at the singularity. So we all know that as brilliant as Einstein was, and as successful as his general theory of relativity has been, it has limits. And one limit is the center of a black hole, and another limit is the very birth of the universe itself.
Regardless of the type of black hole you're talking about, the one concept that always comes up alongside it is that of dark matter. It's a unique kind of matter that outweighs visible matter in the universe. We call it dark because it doesn't interact with light or any other forms of electromagnetic radiation. We know it's there because of how it impacts visible matter and the overall structure of the universe. Many suggest that dark matter had a key role in shaping galaxies and even forming black holes. One of these theories proposes that dark matter acts like a scaffold, with galaxies being built around it. Its gravitational force pulls regular matter like gas and dust together, creating large structures like galaxies. And as these galaxies evolve, the right conditions for black holes to form can emerge. In other words, dark matter, through its gravitational influence, is vital in determining how matter is distributed across the universe. It creates the perfect setting for black holes to form. Another interesting idea is that dark matter could be made up of primordial black holes. If this is true, these black holes would have affected the dynamics of the early universe through their gravitational pull, potentially leading to the formation of more stars and galaxies.
There is a suggestion that the black holes themselves could be dark matter, meaning they are invisible and they could populate the universe almost arguably large enough to explain this missing mass, this missing matter.
Astronomers often watch the paths that stars take around black holes. They do this to spot the presence of dark matter. It has quite an impact on the way stars move within galaxies due to its gravitational pull. One thing that astronomers do is to study the gravitational effects from visible matter, like stars and gas clouds. If the star's motion doesn't line up with what we'd expect from the visible matter alone, it hints at the presence of something more. Perhaps that's where we'd find dark matter. It's important to remember that even though dark matter is seemingly everywhere, it's not typically thought to directly form black holes. Our current understanding is that black holes come about from the collapse of regular matter, like giant stars. But spinning and charged black holes might be related to dark matter in some way. The fact that they spin or carry an electric charge can prolong their existence. This could turn them into a possible source or storage for dark matter particles. It could possibly offer more insights into the character of dark matter and its role in shaping the universe. We come across a compelling interplay between the forces of the cosmos and the counterintuitive rules of the quantum world. In the world of the incredibly small, black holes reveal another puzzling aspect. Stephen Hawking presented a theory that links these two apparent realms: the theory of Hawking radiation. Imagine matter and antimatter particles suddenly appearing near the event horizon of a black hole. Usually these pairs would annihilate each other and disappear. But if one falls into the black hole, the other can escape. This escapee is what we call Hawking radiation. This is basically the gist of this theory. Although Hawking actually described this process more technically, he referred to the positive and negative frequencies of the quantum vacuum that get disrupted by the black hole. This disruption leads to the vacuum itself generating particles that we can detect. Hawking radiation implies that black holes aren't as inescapable as we thought. They slowly lose their mass due to this radiation. This phenomenon helps answer a long-standing question. It was initially believed that nothing could escape a black hole because nothing can move faster than light. However, Hawking radiation led most physicists to agree that the energy sucked into a black hole could eventually leak out.
I think most physicists believe that because you have this Hawking radiation, at least the energy that falls into a black hole can eventually leak away as that radiation. The really important thing about that is that not only can the energy get out, but the information can get out. This was the other perplexing thing about black holes.
Hawking radiation might also help preserve quantum information. This idea was a puzzling aspect of black holes. Quantum information shouldn't be destroyable, and many physicists now suggest that the details of what falls into the black hole could escape through Hawking radiation. If you gathered all the Hawking radiation from a black hole over trillions of years and pieced it together, you could theoretically reconstruct what initially fell into the black hole.
One description of how this happens is that the thing that falls into the black hole somehow gains negative mass or negative energy because the dimensions inside the black hole get all twisted around.
And in a popular interview, we have Brian Cox elaborating on the deeper consequence of this.
If a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in.
And so, what does this actually mean? Could information actually radiate away and get reconstructed through Hawking radiation? So in the final chapter of this compilation video, we're going to delve into the mind-bending topic of black holes' Hawking radiation. When black holes were first conceived mathematically, there's a question arose among physicists. Could these entities actually exist in the universe? The math suggested that they were possible, but was there real-life evidence for it? It took 4 decades before we had tangible evidence. In 1964, using advanced X-ray satellites, researchers detected an unusual source of X-rays in the constellation Cygnus. Despite the intense emissions, the object itself remained invisible. This puzzled the scientists, as a typical star emits both visible light and X-rays. They named this mysterious source Cygnus X1. Kip Thorne and Stephen Hawking even had this famous bet on what the object actually was.
There was a bet between Stephen Hawking and Kip Thorne. Whether or not we actually had the data justified for a black hole. So what was the first black hole?
Stellar mass black hole, so 10-ish suns with a star friend, and the black hole is slowly eating material from the star.
In 1970, astronomers Paul Murdine and Louise Webster observed that Cygnus X1 was in a binary orbit with a nearby star. This relationship allowed them to measure its mass. Fast forward to 2021, it was confirmed that Cygnus X1 has a mass 21 times that of our Sun, making it the heaviest stellar mass black hole that was identified without gravitational waves. The black hole also spins at a rate near the speed of light, faster than any other known black hole at the time.
Louise and I published a paper about the X-ray source Cygnus X1, which might be identified with this system that contained HDE 226868, and if so, and if all connected together in this way that we'd fantasized about, then the companion was a black hole.
Now let's consider again the event horizon of a black hole. As we all know, this is a region where space and time as we know them no longer apply. There's no specific where or when. This concept leads to a curious sight for someone observing from afar as a person is pulled into a black hole. To the observer, the person seems to slow as they near the event horizon, almost as if coming to a halt just before crossing it. He never appears to cross into the black hole, he just fades, growing dimmer until vanishing from sight. This peculiar behavior is due to how black holes distort spacetime. They tie into what's known as the holographic principle. It suggests that all the information within a black hole's 3-dimensional space can be encoded on the 2-dimensional surface of its event horizon. Just like a hologram projects a 3-dimensional image on a flat surface, it must contain enough detail to represent the 3-dimensional space from every viewpoint. The event horizon serves as a repository for information about the interior of a black hole. So to grasp this concept, physicists refer to a framework known as the ADS-CFT conjecture. In essence, this conjecture represents a mathematical concept that describes a special type of spacetime different from our everyday universe. Just think of it as a decipher machine for black hole interiors. It has rules where it explains how things inside the black hole relate to what's on the outer boundary. In a way, this boundary acts like a map of everything inside, just like the hologram concept we talked about. Now, in anti-de Sitter space, big black holes are like eternal entities. They never truly disappear. This is because anything they emit gets reflected back into them, and they continue to exist. On the other hand, small black holes eventually vanish. They can't maintain their existence because they lose more energy than they take in. The thing is, whether it's a big or small black hole, all the information inside them remains intact. None of it just disappears into nothingness. So there's no paradox, and the fundamental idea that information must be conserved in the universe remains valid. Then, when we create a black hole in the context of conformal field theory, we can ensure that this evolution always keeps the information preserved. So information isn't lost, even in the complex world of black holes in anti-de Sitter space. Now this might be the key to unlocking the mystery of the information paradox.
That's a good thing when things go from they often start out as very speculative, then they become something a little bit better than speculative, conjectural. And the end process is they just become a tool of physics. Things that everybody uses all the time because it has a predictive value, a mathematical value.
Apart from their simple structure, black holes are defined by just 3 properties: mass, charge, and spin. This is due to the no-hair theorem, which tells us that the original details of the matter that fell into a black hole are lost, leaving behind only these 3 properties. If you take 2 black holes, one from a massive star and another from a neutron star, they'd appear identical except for differences in their mass, charge, or spin. When we apply quantum mechanics and consider black holes as quantum objects, a whole new array of characteristics comes into play. Take entropy, for example. The entropy of an object is like the number of different ways its insides can be arranged. To figure out entropy, you need to know how much an observer understands about the object. For instance, take a randomly shuffled deck of cards. Describing the position of each card would need a lot of details. We can say that this order has high entropy compared to this one. But the no-hair theorem tells us that we can't get details about the matter inside a black hole. So black holes are thought to have maximum entropy.
As a black hole grows, its entropy increases, okay? So the amount of hidden information increases. And so there's this very tight relationship between actually the surface area of a black hole and the amount of stuff that it's eaten, which corresponds to the amount of information that that black hole is hiding.
Quantum field theory tells us that energy can exist in a vacuum, where pairs of particles and antiparticles pop into existence and then disappear in an instant. So even though we think that the entire mass of a black hole is focused at the singularity, these particle pairs can still appear and vanish within the black hole's vacuum. The process doesn't usually have a noticeable impact if it occurs inside or outside a black hole, except when it happens near the event horizon. In that case, the intense gravity can pull one particle in while flinging its counterpart towards infinity. Since this pair springs from the black hole's energy, the escape of one particle will reduce the total energy of the black hole. This escapee contributes to what we call Hawking radiation. This is quite important for our discussion today. Hawking radiation implies that black holes can emit energy, shrink over time, and ultimately cease to exist. This means that it results in a fundamental loss of information. We lose the ability to pinpoint the precise quantum state of all the particles that once made up the black hole.
If you think of yourself as information, right? Let's say you burn a book and collect everything that comes out of the book, all the ashes and all the gas and everything. Then in principle, you can reconstruct the book. Not in practice, right? But you can imagine if you collect every single thing and measure it, in principle, you can reconstruct the book. Information is conserved in all of physics.
Quantum mechanics says information has to be preserved. But when a black hole gives off energy and eventually disappears, we end up losing something important. Like what exactly made up that thing in the first place? But perhaps there's more to uncover in this story.
So basically, if you can measure everything perfectly, you can predict what happened in the past and what's going to happen in the future. It's called determinism, that, right? So the old picture of black holes, and Stephen Hawking believed this for a long time, had a bet about it actually, is that they seem like they destroy information. You can kind of see it goes to the end of time, right? It's gone. Even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it.
To put it simply, this information could help us map out the entire universe, which enables us to predict basically anything. So a black hole is one such rule breaker, since it doesn't follow the laws of physics as we know them. Once something crosses the event horizon, the information is gone forever, and there's no way to get it back. So to solve this conundrum, scientists have explored various solutions to this puzzling paradox, each providing a possible way to uncover its mysteries. One proposed solution to the information paradox suggests that a black hole holds on to its information until it shrinks to what's known as the Planck size. This scale represents the smallest measure in our universe, sort of like the finest point our cosmic microscope can see. So when a black hole gets this small, it's believed that the stored information gets released all at once. This idea fits with both relativity and quantum mechanics, but it's not without its difficulties. The energy of a black hole at Planck size is incredibly tiny, yet the information packed inside is vast. This leads to a quandary because it seems the information isn't coming out with the radiation, it stays put inside the black hole. For it to release this massive store of information, it would need to emit energy bit by bit, very slowly over time. In fact, it could happen for a much longer time, possibly even outlasting the expected lifespan of the universe. This idea is indeed intriguing. What if all this information could be emitted and survive the lifespan of the universe? Would remnants of it persist into what some refer to as the next cycle of the universe? In 2019, Roger Penrose co-authored a research paper published in the Royal Astronomical Society titled Apparent Evidence of Hawking Points in the CMB Sky. In this study, he and his team reported several anomalies that could indicate a universe that preceded our own. They noted each anomalous spot would have originated from a highly energetic point-like source, resulting from the Hawking radiation of supermassive black holes in a cosmic eon prior to our own. Penrose suggests that some of these supermassive black holes from the previous universe might be connected to the conformally stretched Big Bang of the next eon. The observed anomalies are suggested as evidence of this link, implying that some information from a former universe could influence our current one. So tying this back to the information paradox, this proposed solution hints at the existence of long-lasting black hole remnants, which may prevent us from fully recovering all the information. Now, let's look at another approach based on what we discussed earlier. The entropy of a black hole is related to its event horizon's surface area rather than its volume. Again, it's the so-called holographic principle. According to this, the information of a black hole, while being three-dimensional, doesn't actually plunge into it along with Hawking radiation. It's imprinted onto the event horizon, effectively a two-dimensional boundary. It creates what's known as a stretched horizon. This allows the information to stay in a space where light exists, which avoids any conflict with causality and potentially resolves the paradox. But we still need to keep in mind the no-cloning theorem. It states that information can't be duplicated. At first glance, it seems like this rule is broken, but that's simply not the case. Here's why. Although it appears we have two sets of information, no single observer can ever see both simultaneously. One version is visible only to an observer falling into the black hole, and the other only to someone outside it. This concept is known as black hole complementarity. It suggests that these copies can't be seen or exchanged by multiple observers at the same time. Another intriguing idea is that information isn't lost or contained. It's sent to a separate realm known as a baby universe. Here, the infinite density of the singularity could create such a warp in space-time that it stretches into another universe via what's called an Einstein-Rosen bridge, or wormhole for simplicity. In this scenario, the information tumbling into a black hole could travel through the wormhole and emerge in another universe. This new universe is much smaller compared to ours, and that's why we call it baby universe. Since this other universe is completely separate from our own, any information that crosses over is effectively lost to us but remains preserved there. The appealing aspect of this solution is that it doesn't conflict with any established principles, except for the challenge that we can't really prove this other universe exists. But let's consider this idea. Somewhere beyond the event horizon of a black hole, there might be a path to access this baby universe. So if it is possible, what would be the implications? Physicist Brian Cox suggests that in such a scenario, an extremely advanced civilization could capture all the Hawking radiation emitted, and they'll use it to reconstruct everything that the black hole has absorbed.
If you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out.
Most of our knowledge about black holes comes from studying them in detail, and we've got just the right tools to do the job. This is the Very Large Telescope, or VLT, at the Paranal Observatory in Chile. This observatory houses 4 separate telescopes, each equipped with a primary mirror that is 8.2 meters in diameter. The VLT hosts sophisticated instruments, like the spectrograph for integral field observations. These devices help us observe black holes across different wavelengths, which offers high-resolution images of their dynamics, composition, and their behavior. Then we have the Event Horizon Telescope. It's a unique network of synchronized radio telescopes that are scattered across the globe. When they operate together, these telescopes create an Earth-sized virtual telescope. This configuration enables the Event Horizon Telescope to attain unmatched resolution levels. In 2019, this collaboration took the first direct picture of a black hole's event horizon. This monumental achievement verified the existence of black holes as previously theorized by Einstein. Another tool is the gravity instrument installed at the VLT. By combining light from the 4 VLT telescopes, gravity acts as an interferometer, which achieves incredibly high angular resolution. Its primary function is to investigate the close surroundings of black holes, things like the accretion disks, jets, and gravitational interactions with nearby stars. Assisting gravity is the Extremely Large Telescope, or ELT. Once completed in a few years' time, the ELT will be the largest optical and infrared telescope in the world. It'll boast a primary mirror with a diameter of 39 meters. This impressive size means it will have extraordinary light-gathering capabilities. With advanced adaptive optic systems, the ELT will compensate for atmospheric distortions. This state-of-the-art telescope will play a key role in studying black holes and other celestial phenomena. It will allow us to investigate the growth of supermassive black holes and the relationship between them and their host galaxies in more detail than ever before. Despite our scientific advancements to study a black hole, there's still a great deal we don't know about it, especially the inner workings of this giant beast. Theoretical predictions have provided us with an understanding of their basic structure, but the extreme conditions that exist within a black hole remain largely unexplored. Back in 1985, Carl Sagan was working on a science fiction novel called Contact, which eventually became a well-known film. The plot takes an interesting turn when the main character falls into a small black hole on Earth and emerges from another black hole light years away in space. So that leads us to an intriguing question. Could black holes actually act as gateways to other universes?
When you put like quantum physics and general relativity and you try to come up with some bigger understanding, deeper understanding, string theorists have been all into this, you get a multiverse. We didn't pull that out of our ass, that came out of the equations.
Many theories suggest that black holes could function as natural time machines. This idea is not entirely devoid of scientific reasoning. One key concept is time dilation, which happens because of the incredible gravitational pull that black holes exert. Time dilation comes from Einstein's theory of relativity. It tells us that time doesn't pass at the same rate everywhere, but it can slow down with the increase of gravitational force. This difference in the flow of time between various parts of space-time is enormous near large objects. And so, black holes have become a stage where time dilation is pushed to its limits.
We can definitely travel into the future by moving faster relative to everybody else. And then you'll come back less aged than those you left here on.
Consider the following thought experiment. Imagine a spaceship orbiting a black hole. The crew are so careful not to get pulled in. These guys would experience time moving slower than for those on Earth. When they return, they'd find an Earth that has aged significantly into the future, perhaps hundreds or even thousands of years. Some scientists even suggest that the severe warping of space-time within and around black holes could fold space and time onto itself. This could lead to a closed time-like curve, also known as CTC, or a time loop. A CTC could allow for time travel into the future, and possibly even into the past. This time loop concept proposes that paths exist through space-time that loop back to the starting point in time. But whether such curves exist in our universe is still up for debate. It could have some profound consequences for our understanding of time, causality, and the very fabric of reality.